Bismillah ar-Rahman ar-Rahim. This video is about characterizing a convex function as the pointwise supremum of all affine functions that are global underestimators of the convex function. We have f, this is our convex function, from Rn to the extended set of real numbers. So this is R and plus infinity. The effective domain of the function f is the set D. This is the set of all points in the n-dimensional space where the function f is strictly finite. Here we are interested in a proper convex function f. By proper, we mean that the effective domain is non-empty. So there exists at least one point in the n-dimensional space such that the value of the function at that point is finite, is strictly less than infinity. The epigraph of the function, this is the set of all points in the Cartesian product of Rn and R. We can represent the points in the epigraph as points in the n+1 dimensional space. These are points, if we take the first n components and apply the function f to them, we get a value that is less than or equal to the last component. So the epigraph of function f is the set of all points z in Rn and t in R such that f of z is less than or equal to t. The meaning of the epigraph, if f is a function from R to R, the epigraph is the set of points in R2 that are on or above the curve representing the function. We will assume that function f has a closed epigraph. So function f is a lower semi-continuous function. Thus, our function f is an extended real valued function that can take the value plus infinity. However, the function is proper, which means that at least at one point in Rn, the function is finite. So the function is proper and its effective domain is a non-empty set. The function is lower semi-continuous, which means that the epigraph of the function is a closed set. Note that because the function f is proper, the epigraph is a non-empty set. Because there are values in Rn such that the value of the function is strictly finite, and so you can find points in Rn plus 1 satisfying this inequality. The function being proper implies that the epigraph is non-empty. There is a known result in convex analysis, which is that the function is convex if and only if the epigraph is a convex set. And this can be checked in a straightforward way. Suppose that we take 2 points, z1 and z2 in Rn, such that f of z1 is less than or equal to t1, which is a real number, and f of z2 is less than or equal to t2, which is a real number. So this means that z1, t1, and z2, t2, these are points in the n+1 dimensional space. Both these points are in the epigraph of function f. Now, what about the point that is a convex combination of these 2 points, lambda z1 plus 1 minus lambda z2, and lambda t1 plus 1 minus lambda t2? Is this point in the epigraph? Because if it is for any lambda between 0 and 1, then indeed the epigraph is a convex function. And yes, it is. What is f of this quantity? F of lambda z1 plus 1 minus lambda z2. Because f is a convex function, then by definition this is less than or equal to lambda f of z1 plus 1 minus lambda f of z2. But f of z1 is less than or equal to t1, and f of z2 is less than or equal to t2. And so we have that f applied to the first n coordinates in this vector in Rn plus 1 is less than or equal to the last component. So indeed, if f is a convex set, then the epigraph is a convex set. Set A is the set of all affine functions from Rn to R. So those are the functions in this form, alpha transpose x plus beta, and alpha is in Rn and beta is in R. Okay, so those are the functions that looks like alpha 1 x1 plus alpha 2 x2 all the way to alpha n xn. Here I am assuming that vector alpha has components alpha 1, alpha 2 to alpha n, and vector x has components from x1 to xn. This is the inner product, so it is alpha 1 x1 plus alpha 2 x2 all the way to alpha n xn plus beta, which is a real number. All functions with this form are the affine functions from Rn to R. Those functions are the elements of set A. Now set AF, A sub f, those are the affine functions from Rn to R, such that for every x in Rn, A of x is less than or equal to f of x. So this set AF is the set of all affine functions that are global underestimators of the function f. Is this set guaranteed to be non-empty? We will have to show this. And then we need to show that the function f of x is equal to the supremum of the functions A of x taken from this set. And this is true for every x in Rn. This is the main result in this video, which is that the function is the pointwise supremum of all affine functions that are global underestimators. We have two tasks: to prove that the set AF is non-empty, and then to prove this statement here. To proceed, we need a separation theorem. In order to prove our theorem, I will take for granted the following result. Set S is a subset of Rm, and set S is non-empty, closed, and convex. So this is set S. There is a point in Rm which is x. We define the distance between x and s as the infimum of the L2 norm of x minus z, where z is in S. We measure the distance, the Euclidean distance between x and every point in S. We compute the infimum. By definition, this will be the distance between x and s. The projection of x onto set S is the set of points in S, such that the distance between x and z is the distance, is equal to this infimum here. For a general set S, this set here may be empty, or it may have infinitely many elements. For example, if we take S to be the points in R2, such that the L2 norm of the point is strictly less than 1. We are talking here about the open disk with radius 1, and let's take X to be this point 2 and 0. So here the radius is 1. What is the distance between X and this disk? Well, we can compute the distances, and the infimum will be 1, which is this length here. However, there is no point in the set S such that the Euclidean distance between x and z is equal to 1. And this is because this set is not closed. In our case here, the distance is unity. However, the projection set is empty. Now take S to be the set of points in R2 such that the L2 norm of z is greater than or equal to 1. And take X to be the origin, 0, 0. In this case, this is the set S. And here is X. What is the distance? The distance is 1. And all the points on this circle with radius 1 are points in S that satisfy this relationship. The distance between x and z is equal to 1. So the projection set may be empty, or it may contain infinitely many points in set S. However, if S is non-empty, closed, and convex, there is a unique point in S, denoted here by z tilde, such that the Euclidean distance between x and z tilde is equal to this infimum, which is the distance between x and s. This set will be a singleton. It will have exactly one element if set S is non-empty, closed, and convex. Now, let's consider a point x that is outside the set S. This implies that the distance between x and s is strictly positive. Since x does not belong to S, then the L2 norm squared of x minus z tilde, which is the projection of x onto set S, this L2 norm squared is strictly positive, and by definition this is less than or equal to the L2 norm squared of x minus w for every w that is in the set S. W is written here as lambda z plus 1 minus lambda z tilde. Is this a point in the set S? Yes, because z is a point in S, z tilde is a point in S, and S is a convex set. If there are 2 points in S, then a convex combination lambda z plus 1 minus lambda z tilde, where lambda is between 0 and 1, this is also in S. Here I will exclude 0 for a reason that will become obvious shortly. So I will take lambda to be strictly greater than 0, less than or equal to 1. Rewrite this term here as x minus z tilde plus lambda times z tilde minus z. Expand this L2 norm squared. This is the Euclidean distance squared between x and z tilde, the L2 norm squared of this vector. And then we have the L2 norm squared of that vector. The scalar lambda can be taken outside as lambda squared. And then we have here the L2 norm squared of z tilde minus z. And then we have the cross term. This will be 2 times the inner product of these two vectors. So this is 2 lambda, and then x minus z tilde transpose times z tilde minus z. You can see that this term is exactly like this term, so they can be cancelled. And then we can move this term to the other side. I used the minus sign to write this as z minus z tilde. This 2 lambda times the inner product is less than or equal to this term here. Because lambda is assumed to be strictly positive, we can divide both sides by 2 lambda. Thus we have x minus z tilde transpose times z minus z tilde. We have this inner product less than or equal to lambda over 2 times this L2 norm squared of z tilde minus z. Take the limit of both sides as lambda approaches 0 from above. This left-hand side is independent of lambda, so the limit of this left-hand side is itself. And then on the right-hand side, there is a lambda. And if we take the limit as lambda approaches 0 from above, this right-hand side tends to 0. We have now the following inequality. The inner product between this vector and this vector here, this inner product is less than or equal to 0. In this bracket, add and subtract x. So write it as z minus x plus x minus z tilde. Then do the multiplication. We will have x minus z tilde transpose times z minus x plus x minus z tilde transpose times x minus z tilde. This is the L2 norm squared of vector x minus z tilde. And this vector is here. This is less than or equal to 0. Now move this to the other side, and I used the minus sign to write this as z tilde minus x. The inner product of z tilde minus x and z minus x is greater than or equal to this L2 norm square, which is strictly positive because this is the square of the distance between x and set S, and we have assumed that x is not an element of this non-empty closed convex set S. Now we have our result. Let's call this y. What do we have? We have y transpose times z minus x is greater than or equal to a strictly positive quantity, c. This is what we have. This means that y transpose z minus y transpose x is greater than or equal to c, which can be written as y transpose z is greater than or equal to c plus y transpose x. And this is true for any z in set S. The conclusion is that there exists a vector y. Specifically, this vector is z tilde minus x. This vector is the projection of x onto S minus x. There is this vector that satisfies the following inequality. The inner product between this vector and any vector in the set S is greater than or equal to a strictly positive number c plus the inner product between that vector y, which is z tilde minus x, and x, the point that is not an element of S. And of course, this right-hand side is strictly greater than y transpose x. So there is a vector in Rm such that the inner product between this vector and every vector in set S is strictly superior to the inner product between the vector and x, a point that is outside S. So far, we have function f that is convex, proper, with a non-empty effective domain. It has an epigraph that is closed. We have set A, the set of all affine functions from Rn to R, and our interest is set AF. So this is the set of all affine functions that are global underestimators of the function f of x. Consider x bar in the effective domain of function f. This means that f of x bar is strictly finite. Take the point x bar and gamma. So x bar is n-dimensional, gamma is a scalar that is not in the epigraph of function f. This means that f of x bar is strictly greater than gamma. We have a separation theorem from the previous page that if there is a subset of Rm non-empty, closed, and convex, and there is a point u in Rm that is not in S, then there exists a vector, a non-zero vector, and a positive real number eta, such that V transpose Z, and this statement is true for every Z in this non-empty closed convex set S, V transpose Z is greater than or equal to eta, this positive number, plus V transpose U, the vector that is not a member of set S. In our case, we have this vector here in Rn plus 1. This vector is outside the epigraph of function f of x. And is the epigraph non-empty? Yes, because function f is proper. It has a non-empty effective domain. There is at least an x bar in Rn such that f of x bar is finite. Is the epigraph closed? Yes, by assumption. We had assumed that function f is lower semi-continuous, and this is equivalent to the epigraph being a closed set. Is the epigraph convex? Yes, because function f is convex. Consequently, we can apply this result here. The epigraph is like our set S, and this is the point outside the set. There is a vector, a non-zero vector, in Rn plus 1. The first n components of the vector are y tilde, and the last component is the scalar un plus 1. There is a positive real number eta, such that the inner product between this vector and any vector in the epigraph of function f is greater than or equal to eta plus the inner product between this vector and that point that is outside the epigraph, which is the point x bar and gamma. Every point in the epigraph is represented as this vector. The first n elements are x, and then the last element is f of x plus a non-negative real number. For a point to be in the epigraph, we want the function f applied to the first n components to be less than or equal to the last component. So here we will write down the last component as f of x plus a non-negative real number. This vector represents vectors that are in the epigraph of function f, and this is true for every alpha that is a non-negative real number. If we do this inner product, then we have y tilde x plus the scalar yn plus 1 times f of x plus alpha, this is greater than or equal to eta, then this inner product is y tilde transpose x bar plus yn plus 1 times gamma. And this should be true for any x in the effective domain of function f. This is the inequality that we have, and it is true for every x that is in the effective domain of function f. It is true for every alpha that is non-negative. It is true for every gamma such that gamma is less than f of x bar. And x bar is a point in Rn that is in the effective domain of the function f of x, and eta is a strictly positive real number. In this inequality, we can put x equal to x bar. If we do this, on the left-hand side, we have the inner product of y tilde and x bar. We have the same term on the right-hand side. So these two can be cancelled when we put x equal to x bar. The inequality becomes yn plus 1 times f of x bar plus alpha greater than or equal to eta plus yn plus 1 times gamma. If we put yn plus 1 equal to 0, we don't have problems. On both sides, we have 0 times a finite number. This is a finite number because alpha is a non-negative real number, and f of x bar is finite because x bar is in the effective domain of function f of x. And gamma is a real number that is strictly less than f of x bar, and f of x bar is strictly less than infinity. So the numbers multiplied by yn plus 1 are finite numbers. If we put yn plus 1 equal to 0, the left-hand side is 0, and this term on the right-hand side becomes 0, and we get the inequality 0 greater than or equal to eta. This inequality is incorrect. It is false because eta is a positive number. So yn plus 1 cannot be equal to 0. Recall that we have a separation theorem, and the separation theorem tells us that there is a vector y, and the vector y, the inner product between vector y and any vector in the epigraph of function f, is greater than or equal to eta plus the inner product of vector y and a point that is outside the epigraph of function f. The point that we have is x bar, and then gamma chosen to be strictly less than f of x bar. Vector y itself, which is a vector in Rn plus 1, its first n components are y tilde, and yn plus 1 is the last component. Our conclusion is that this last component here cannot be equal to 0. It must be non-zero. Can it be strictly negative? Suppose it is. And divide both sides of this inequality by yn plus 1. The left-hand side becomes f of x bar plus alpha. Since we have divided by a negative number, then the inequality is reversed. The right-hand side becomes gamma plus eta over yn plus 1. Note that this inequality must be true for every non-negative alpha, but this cannot be true. Those numbers are fixed, gamma, eta over yn plus 1, and f of x bar. But this inequality should be true for every alpha, no matter how large. However, for sufficiently large alpha, this inequality cannot be true. So if we push alpha towards infinity, this inequality will be violated, but it needs to be valid for every non-negative alpha. We can also reject this possibility that yn plus 1 is strictly negative. Based on these two arguments, we are sure now that the last component in this vector y must be strictly positive. Divide both sides of this inequality by yn plus 1. We get this inequality here. Note that this inequality here, because this term is strictly positive, eta is strictly positive, yn plus 1 is strictly positive, this quantity here is strictly greater than 1 over yn plus 1 y tilde transpose x bar plus gamma. This inequality here is true for every non-negative alpha. We can put alpha equal to 0, and we can take this term and move it to the other side of the inequality. We get that f of x, and this is true for every x in the effective domain of the function f, is strictly greater than. Then we have this vector transpose times x plus this vector transpose times x bar plus gamma. If we examine the right-hand side, it is an affine function. This is c gamma of x. It is an affine function, alpha tilde transpose x plus beta tilde. Beta tilde is this scalar here, and alpha tilde is minus y tilde divided by this scalar, the positive real number yn plus 1. We have f of x is strictly greater than, and so it is greater than or equal to this affine function, which is parameterized by gamma. Using the separation theorem, we were able to find an affine function that is a global underestimator for the function f of x. Recall that if x is not in the effective domain of the function, then f of x is plus infinity. So there is no worries here. For every x in Rn, we have f of x greater than or equal to this affine function. the existence of this affine function follows from applying the separation theorem. The conclusion is that the set AF, the set of affine functions that are global underestimators of the function f of x, this set is non-empty. We can now show that for every x in Rn, f of x is the supremum of all those affine functions in the set AF. Recall that the set AF is the set of all affine functions, and those affine functions are global underestimators of the function f. Fix x bar in D, so x bar is in the effective domain, f of x bar is a finite number. By definition, every affine function in this set AF will satisfy that ax bar is less than or equal to f of x bar. So f of x bar is an upper bound on ax bar for every a that is in this set. But to show that f of x bar is a supremum, we need to show that for every epsilon greater than 0, we can find an affine function, let's say g of x, that is in the set AF, and g of x bar is strictly greater than f of x bar minus epsilon. This part here, we show that f of x bar is an upper bound, but to show that it is supremum, we need to show that it is the least upper bound. And to show that it is the least upper bound, we need to show that for every positive epsilon, we can find an affine function in AF, and this affine function is strictly superior to f of x bar minus epsilon, no matter what epsilon is. For every x in the effective domain of the function f of x, we know that f of x is greater than c gamma of x, as we did on the previous page. Now, gamma is any real number that is strictly less than f of x bar. Recall that to apply the separation theorem to the epigraph of function f of x, we needed a point outside the epigraph, and this point was x bar and then gamma. And for this point not to be in the epigraph of function f, we needed f of x bar to be strictly greater than gamma. This result here is valid for any gamma, so long as it is strictly less than f of x bar. For every epsilon, we can choose gamma to be f of x bar minus epsilon over 2. This is strictly less than f of x bar. So we have an affine function, c gamma of x, and this affine function, it has these two terms, so minus 1 over yn plus 1 y tilde, all transpose times x minus x bar. And then we can set gamma equal to f of x bar minus epsilon over 2. What is the value of this function at x bar? If x is equal to x bar, this is 0. And the value of the function, the affine function, is f of x bar minus epsilon over 2, the value that we gave to gamma. And this is strictly greater than f of x bar minus epsilon. Given x bar and f of x bar, since we have this family of inequalities that are valid for every gamma that is strictly less than f of x bar, given any epsilon, we can just make this a choice and have an affine function such that the affine function evaluated at x bar is greater than f of x bar minus epsilon. For every x bar in D, for every epsilon that is strictly positive, we can have an affine function living in the set AF such that the function evaluated at x bar is greater than f of x bar minus epsilon. This result here and c gamma of x bar being less than or equal to f of x bar mean that f of x bar is the supremum of a of x bar, where a is in the set AF. But what if x bar is not in D, is not in the effective domain of function f? In other words, f of x bar is infinity. So we want to show now that the supremum at the points x that are not in the effective domain of function f, the supremum is infinity, which means that we can find affine functions in the set AF such that their values at x bar can be arbitrarily large. This is our previous result. This inequality here, this was obtained assuming that x bar is in the effective domain. This inequality is true for every x in the effective domain, for every non-negative alpha, for every gamma strictly less than f of x bar. We need to do a modification. X bar now is not in the effective domain, f of x bar is infinity. Because of this, any point x bar and gamma will not be in the epigraph of the function f. Gamma is not constrained. In our previous result, gamma is less than f of x bar. Now gamma is any real number. But we cannot set x equal to x bar because x is in the effective domain and x bar is not in the effective domain. So this is the inequality that we have now. Gamma can be any real number. We cannot put x equal to x bar. Can yn plus 1 be negative? Like in the previous case, no. If we divide by yn plus 1, this inequality will be reversed. And the left-hand side will contain alpha, and the inequality should be true for any non-negative alpha. But we have numbers. F of x, for example, is a finite number. X is in the effective domain of the function, and so on. and we can push alpha towards plus infinity. We can choose alpha to be arbitrarily large. For a sufficiently large alpha and an inequality in this direction, the inequality will be violated. So yn plus 1 cannot be negative. It can be positive. And if it is positive, we can divide by it, and we get the inequality 1 over yn plus 1, y tilde transpose x plus f of x. We can put alpha equal to 0. It is non-negative, so I can put alpha equal to 0 now. The inequality is sustained. In this case, we are dividing by a positive number. Then we have eta over yn plus 1, then 1 over yn plus 1, y tilde transpose x bar plus gamma, like this. Move this to the other side. And because this is a non-negative quantity, we can lower bound by these two guys minus this term, as we can see here. This is our C gamma of x. Gamma is any real number. C gamma of x bar is gamma. There's nothing now preventing us from assigning a very large value to gamma. We have functions in the set AF, and at x bar, if x bar now is not in the effective domain of the function, we can find functions that can be made arbitrarily large at x bar. This means that the supremum is infinity, and this is exactly what we wanted to show. We cannot now exclude the possibility that yn plus 1, the last component in this y vector obtained via applying the separation theorem, we cannot exclude the possibility that it is 0. If yn plus 1 is 0, then this term will disappear, and also this term. The inequality becomes y tilde transpose x greater than or equal to eta plus y tilde transpose x bar. X is in the effective domain, f of x is finite, x bar is not in the effective domain, f of x bar is plus infinity. Move this to the other side and rewrite the inequality as y tilde transpose x bar minus y tilde transpose x plus eta less than or equal to 0. Consider function d0 of x. It's an affine function that is taken from the set AF. This means that d0 of x is less than or equal to f of x for every x in Rn. d0 of x is a global underestimator of our function of interest f of x. Define d zeta of x as d0 of x, this affine function, plus we add zeta, which is a non-negative real number, and we multiply zeta by this bracket here. Note that what we have here, we have zeta y tilde transpose x bar, that's a constant. We have zeta eta, that's a constant. We have minus zeta y tilde transpose x, that's a linear function of x. In other words, d zeta of x is still an affine function. Is it an affine function in the set AF? The answer is yes, because this quantity between brackets is non-positive and zeta is non-negative. So this term here is non-positive. D zeta of x is less than or equal to d0 of x, which is chosen from AF, so d0 of x is less than or equal to f of x. Thus, for every x in Rn, d zeta of x is less than or equal to f of x. D zeta of x is a function in the set AF. What is the value of this function when evaluated at x bar? D zeta of x bar is d0 of x bar, which would be some real number, plus if we put x equal to x bar, these two terms cancel, and we are left with zeta times eta. Eta is a positive number. Zeta is a non-negative number, and it's arbitrary. For every non-negative zeta, d zeta of x is in the set AF. We can choose zeta to be as large as we wish. Consequently, there are affine functions in the set AF. Those affine functions can be made arbitrarily large when evaluated at x bar, which is not in the effective domain of function f. This finishes the verification that for every x in Rn, f of x is indeed the supremum of the affine functions that are in the set AF, the set of affine functions that are global underestimators of f of x.